Welcome back, guys. Finally, we're at the last part of chapter number 5. I just figured it'd be a little bit easier to break it down into 4 parts so that we can take our time to go through some of these things. And so we ended up last time talking about gas evolution reactions. So now what we're going to do is we're going to talk about something known as oxidation reduction reactions. Oxidation reduction reactions occur because electrons are actually transferred from one element to another. And so these are also known as redox reactions is the short term. So I'll be probably saying redox reactions instead of oxidation reduction, reduction oxidation reactions. And so what we're going to see is there are some specific rules that we have to abide by when we talk about reduction and oxidation reactions. We'll talk a little bit about the 3 different types or at least the 2 major types of reduction oxidation reactions that we would probably look for or look into. And then we'll probably be done with chapter 5. Oh, thank you. So here are some specific rules about the transfer of electrons. Okay, so we're going to talk about oxidation. We're going to talk about reduction. Oxidation is the loss of electrons. So if something it loses an electron, it becomes oxidized. If it gains an electron, right? So if something loses an electron, another thing has to gain an electron. That thing then is being reduced, or that is the reduction. So I have 2 pictures here on the slide for a perfect example of a memory trick that we can use, a mnemonic that we can use to help us remember this. You have oil rig on the right. Oil rig, oxidation is loss, reduction is gain, right? So oxidation is loss, the reduction is gain. I also have a Liger. If you've ever seen the movie Napoleon Dynamite, congratulations. If you haven't, I would recommend it. But they draw a Liger. It's not Liger, it's Leoger, L-E-O-G-E-R, to where we have loss of electrons is oxidation, gain of electrons is reduction. Whichever one you want to use is fine, but we just have to be sure that we know that oxidation is loss, reduction is gain, because you will be asked which species or which element is being oxidized in a reaction and which one is being reduced. And so let's talk about some more rules about this oxidation reduction reaction. Oxidation, the way this works is the ones at the higher up, so number 1 outdoes number 2, number 2 outdoes number 3, so on and so forth. When we are going to assign what's known as oxidation states, these are the charges of atoms within a compound, within a molecule, right? We talk about in sodium chloride, sodium is +1, chlorine is -1. Those are their oxidation states. We just weren't ready to use that term when we were doing it. So you guys have already been doing this. Now it's just time to assign some rules to it and actually put a name to it. And so here are the rules, and we'll show you how this applies in the real sense of things. And so there are rules for assigning oxidation states. Rule number 1, and the oxidation state of an atom in a free element is always 0. So if you have copper solid, if you have iron solid, if you have chlorine gas, if you have bromine gas, all those are in their elemental states. If you see an elemental state, you know the charge is 0. If you look at a reaction and you see something in its elemental state, light bulbs, sirens, horns should go off in your head saying, hey, this is an oxidation reduction reaction. The oxidation state of a monoatomic ion. So let's say we just see Na+1. The oxidation state is equal to its charge, right? Pretty self-explanatory. The sum of oxidation states in an atom is equal to, if it's a neutral ion or a neutral atom, it's 0, right? So when we talk about NaCl, the total charge on that molecule or formula unit is 0. And so the oxidation charge of sodium and chlorine have to equal to 0. Now, if it is an ion, so let's say SO4 -2, the total ion charge has to be -2. Number 4, in compounds, metals always have positive oxidation states. We talked about this before, right? Metals are always becoming cations, giving up their electrons. Group 1A, the alkali metals are always +1. group 2, the alkali earth, are always positive 2, right? That we need to just memorize. We just need to know that for sure. Number 5, in their compounds, nonmetals are assigned oxidation states according to the table, which we'll look at in the next slide. Entries at the top of the table, again, take precedence. So let's look at this table and we'll walk through this, and then I will show you how we can use this in real life. The oxidation states of any given element generally depend on what other elements are present, right? And so fluorine is -1, hydrogen is usually +1, oxygen, we said, is usually -2. We'll look at this a little bit. Group 7A, -1, 6A, -2, 5A, -3, depending again on what it is bound to, it will determine what oxidation state it is, and that's key. Rule number 3 must always be followed. Rule number 3, remember, is that whatever the charge was, if it's neutral, it's 0. If it's not, if it's an ion, then that's the total charge, and that'll determine. When assigning oxidation states to elements that are not covered by rules number 4 and 5, such as carbon, right? Carbon's not in there. We just, you look at the total charge and you just kind of predict what their oxidation state is based on other things that we know for a fact, and those that are preceding. So let's talk about this, right? Let's talk about this in the context of maybe assigning some oxidation charges, as well as looking at the 3 different types of chemical reactions that are more likely to be reduction oxidation reactions. So let's go ahead and look at this. So there it goes. For some reason today, this does not want to stay up. So let's look at CO2, right? And I want to know what the oxidation state is of both of those. So now if we remember, CO2, oxygen, according to rule number 5, is -2, right? There's nothing preceding this, and so we can feel confident that oxygen is -2. So in that case, we know we have 2 of them, so there's going to be a -4 total charge. Well, based on rule number 5, or that's rule number 5. Now we said with carbon, we don't really know because it's not there, but we said since this is a neutral, right? Since this is a neutral, let me write it lower, right? Neutral compound, right? There's no charges on it. That the total charge has to then be 0. So we know this carbon has to be +4. Usually you'll see that. Usually you'll see carbon at +4, but we just have to check on the other elements that it's bound to. So that's carbon. Let's look at the SO4 -2. So again, we know, we would assume, right? So let's say we would assume that this is -2, right? And based on the table that we saw just previously, sulfur goes in group 6A, we would assume this is -2. Well, we're already looking at a problem, right? Because we know that there's a -2 overall charge. So if we have a -2 from the oxygen, -2 from the sulfur, that's going to be at least -4. And let alone we now have 4 oxygen, so we can multiply this by 4, and that's going to be -8. So now we're looking at -10. So remember the rules. Oxygen comes before sulfur in that table. And again, this will come with practice. This will come with practice and constantly looking at these things. And so we'll say this has to be -8. Well, based on rule number 3, we have to have a -2 overall charge. If we have a -8 here, then sulfur has to be a +6. And in this case, that's actually exactly what happens. And so just again, it's all about looking at the things that are around it. Now, we're talking about rules and what rules come first. Here's a compound, K2O2. And based on the previous examples, our first inclination is to take this, make it -2, make this +1, right? Because potassium is always +1 times 2. This is going to be +2. This is going to be -4 because we multiply that by 2. Well, this is a neutral element, or neutral compound, excuse me. So +2 -4, oh, there's a -2 charge. Well, if we looked at the table, rule number 4 tells us that potassium is always +1. Rule number 5 tells us that oxygen is dependent on some other things. And so in this case, oxygen has to be -1, right? So again, I'm not going to give you anything like that, right? If you see oxygen, it's probably going to be -2 always. But I just want to show you guys maybe a caveat or something to just kind of think about. So let's talk about the 3 different types of reactions. So there's synthesis. Let's do this. Synthesis, where you usually take 2 elements, as you can get H2 gas plus O2 gas goes to H2O gas or liquid, it doesn't matter, right? So where you take 2 elements and you combine them. You have decomposition, right? Decomposition where you take, let's see. Let's just do that in reverse, right? Right, where you take a compound and you turn it into its elements, or we have a single displacement. Right, and a single displacement is usually where you have an element plus a compound, and you go to another compound plus an element. Oh, we'll just do it this way, just for the sake of example. Right, plus an element, right? So what do all these 3 reactions? It doesn't matter what the kind is, all have something in common. And here again is the pattern, and we need to see the pattern. And the pattern is you see something in its elemental state. Right? You see something in its elemental state. If you see something in its elemental state, then we should be aware that it is going to be a redox reaction. All right. Apparently the board wants to lay down, and that's okay. We all need a rest sometimes. Actually, let's go with it. All right. So let's go ahead and finish up chapter 5 just by talking about, okay, how can we now determine if something is oxidized or reduced? Okay, here's how. We look at the equation and we then calculate oxidation states. So calculate the oxidation states of each element. And if this isn't a redox reaction, then you have to have something that's reduced and something that's oxidized. So oxidized, so in this case we have carbon plus sulfur. Very similar to what you guys did in the first experiment. And we make this compound, copper sulfide, or yeah, copper disulfide. And so we know that we combine these, right? And so then we can calculate charge states. We've already talked about this of the compound, and we know that these elements are at 0. And so then we just have to see which one gains an electron. So if you gain an electron, you're going to become more negative. If you lose an electron, you're going to become more positive. And so this carbon becomes more positive by losing an electrons. Remember, oxidation is loss. So this is what becomes oxidized. The carbon becomes oxidized. The sulfur becomes reduced because it gains those electrons. Now, one of the things that we need to be aware of, right, is so that the copper loses the electrons to the sulfur. So copper loses electrons to the sulfur. The copper is the reducing agent, right? It reduces the sulfur, or it causes the sulfur to be reduced. So the reducing agent is always oxidized and the oxidizing agent is always reduced. Now, that's kind of confusing, I understand, but it makes sense if you think about what they're actually doing in the reaction. Okay, so I want you guys to practice this a little bit. Just walk through some of the problems in the book. If you have any questions about the rules or any questions about how to do this, please let me know. There is one more type of equation that we'll go ahead and talk about. just to bring up combustion reactions. It's a reaction with a substance in O2 to form one or more oxygen-containing compounds. These are notoriously difficult to balance. I am not going to make you guys balance a combustion reaction on the exam, but I do have to just tell you, we've already seen them before in a math equation, and so I just want to let you know what a combustion reaction is. This ends chapter 5. Chapter number 6 we will do shortly. Chapter 6 we'll be dealing with gas laws. So we move from liquids here in aqueous solutions to gases.